Welcome back to my channel, dear students. So today we are going to continue our work on continuity and differentiability. So far we have seen in our first part and second part, we have seen continuity. Now in this particular lecture, we are going to talk about differentiability. Okay, so let us start with the definition of differentiability. Now we'll first talk about differentiability of a function at a point. So the definition is somewhat like this. Suppose f is a real valued function. Okay, so f takes only real value and c is a point in its domain. So c is a point in its domain. Now function f is differentiable at c if the following limit exists. That means if this limit exists, then the function is said to be differentiable at point C. Okay, now this limit exists means the left hand limit and right hand limit should be equal. Now in this case, instead of calling it to be left hand limit and right hand limit, I'm going to call it left hand derivative and right hand derivative. Okay, so that is, this limit exists if left hand derivative is equals to right hand derivative. Now what's left hand derivative? Let us see what is my left hand derivative and right hand derivative. So left hand derivative is given by limit x tends to c minus, and the same function is written, and this in turn can also be written in this way. How? This will be explained when we are doing sums. Now right hand derivative, similarly here we have to write c plus and everything will be same. And another definition for right hand derivative is this much. And how we have obtained these two, this will be explained later in a sum. So pause the video to note down the definition. Okay, one more thing I want to say here is the derivative of y equals to fx is represented by f dash of x, okay, or dy by dx. Now let's see the geometrical interpretation of differentiability of a function at a point. Okay, so we are going to talk about geometrical interpretation, so that's why I've taken xy coordinate system here. Now I'm going to plot my graph here. So let me take y equals to fx to be this curve. Now this gives me from here to here is my domain. Okay, from here to here is my domain. Now let me choose a point C in its domain. So in this I'm going to choose a point C. So this is my point C, let me assume. Now if this is C, then its corresponding y value, because when it is x, it is y value is fx. So that's why when the value of x is c, the y value will be fc. So that's why this is my fc. So this being fc means this height is fc. Similarly, now let me call this point to be p. Okay, now I'm going to introduce a very small quantity h, which is positive. Okay, so if h is very small quantity, which is positive quantity, then this, see, from here to here is h. Okay, from here to here is also h. So till here is c. So that means from here to here is c. So that's why from here to here is going to be c plus h. Okay, and if I remove h, because from here to here is h, so if I remove h from c, this point becomes c minus h. So this is my c plus h and this is my c minus h. So similarly the corresponding y value will be given by, okay, for first let me call this point to be a and let me call this point to be b. So the corresponding y value will be given by f of c minus h, and this will be f of c plus h. Okay, now let me join a and p. So it is line AP. Okay, now let us find what is the slope of line AP. Here the coordinate of A is c minus h comma f of c minus h, x comma y. X is c minus h and y is f of c minus h. Okay, so Similarly, the coordinate of P is given by C comma f of C. That's why the slope of this line is given by y2 minus y1 by x2 minus x1, okay, which is this much, right? And here actually here it should be C, because this is x2 minus x1, so x2 is this one and x1 is C, so here it has to be C. So this minus C and plus C gets cancelled, so you have minus h in the denominator, and whatever is left, that is nothing but my left hand derivative. Okay, now similarly let me join PB, and if I find the slope of this line, see the coordinate of this will be C plus H comma f of C plus H. Okay, so similarly if I find the slope of this, I'll have this one, and similarly this is also C. This C and C gets cancelled, so only H will be left, and whatever we get after cancellation, that will be my right hand derivative. Okay, so we have founded the slope of this and we have founded the slope of this. Now as I said earlier, H is very small positive quantity. Now let's see what happens when H becomes 0. H is tending towards 0 means a small positive quantity is trying to become 0. So that means this distance is trying to become smaller. Trying to become 0 means it is trying to come this way. Similarly, this H is trying to come this way. Okay, so when it happens, this line also tries to come this way. Okay, and this line also comes till here. Okay, and it seems like a single line when H becomes very small, right? So when it happens, then the very same line becomes a line like this, which is nothing but a tangent to the curve at point P. Hope you are able to understand. So that's why my derivative of a function at point C gives me the slope of the tangent. Okay, because all these are slope of the lines. Okay, so this is my left hand derivative, this is my right hand derivative, and they are trying to become equal here. So the derivative at a point C gives me the slope of the tangent drawn at that point. So that's why derivative of function at a point gives the slope of the tangent drawn at that point. So hence f dash of C represents the slope of the tangent to the curve y equals to fx at x equals to C. So pause the video to note down. Okay, dear students, now after understanding differentiable functions, we'll move on to prove the first theorem of this particular topic. Now the theorem says every differentiable function is continuous, okay, but the converse is not true. That means we are going to show that every differential function is continuous, okay, and to prove that the converse is not happening, we'll take counter example. Now let us see the proof part of the first sentence, that is every differentiable function is continuous. Now I'm going to assume let f be a differentiable function. Now if f is differentiable, then we know that this limit exists. Yes, we know that this limit exists, and the value of this will be equals to, this limit will be equals to f dash of x. Okay, so let f be a differential function at C, at point C. So then what happens? Then we have f dash of x equals to limit x tends to C fx minus fc by x minus c. So let me call this as equation 1. Okay, now we know that this can be written as, now we know that we have fx minus fc equals to fx minus fc, which is quite obvious. Now I'm going to do one small manipulation out here. So what am I going to do is, we have the same thing again, so fx minus fc, right? Now I'm going to divide here by x minus c, and again I'm going to multiply it by x minus c, so both means the same. Now I'm going to put limit on both sides. Okay, so applying or taking limiting value, so limit x tends to c on both sides. So let's see what happens. So if I put this one on both the sides, then we have limit x tends to c fx minus fc by x minus c. Now since there is into here, this limit can be applied here as well. So we have limit x tends to c x minus c, and here we have limit x tends to c fx minus fc. Okay, now obviously this is equals to how much? This is equals to, from 1 it is f dash of x, so this can be written as f dash of x into, okay, so this is limit x tends to c x minus c. So let me put the value of x to be c, then I'll get c minus c, right? Okay, so from here I'll get limit x tends to c fx, I'm just opening the bracket. Now when I keep this limit with this, there is no x here, so that's why there is no use of this limit out here, so this can be directly written as fc. Okay, now c minus c is how much? It is 0, right? So 0 into f dash of x is already 0, so this is 0, and here we have limit x tends to c fx minus fc. So from here what am I getting? I'm getting, let me take this out there, then I'll get limit x tends to c fx equals to fc. Now what is the meaning of this? This means that the function is continuous at c. So pause the video to note down. Now we'll try to prove the converse, that is, every continuous function is not differentiable. Now to prove this, okay, to prove this I'm going to take a counter example, and for counter example I'm going to take a function fx equals to mod x. Okay, so we'll write consider fx equals to this one, and we know the definition of model's function, that is x if x is greater than or equals to 0, and minus x if x is less than 0. So this is the definition for your modulus function. Now from continued chapter we already know that mod x is a continuous function. If you are not aware of that, then we'll have a look at it once again. So we are checking continuity. So we will check continuity in one side, we'll check differentiability on other side. So differentiability on other side. Now to check my continuity, I need to show that left hand limit is equals to right hand limit, and this is equals to functional value, that is f of c, and c here is 0 because the function is breaking at 0. So I'll show this, okay, and to prove differentiability I'll check whether left hand derivative and right hand derivative are equal or not. If they are equal, then the function is differentiable. If they are not equal, then the function is not differentiable. So let's check this particular thing. Now left hand limit. So left hand limit is given by limit x tends to c minus, that is 0, minus fx. That means this x is approaching 0 from the left side, so that's why this x is less than 0. Okay, so let me draw the diagram and show. So this is my 0, and x is approaching to 0 from left side, so that's why whatever number comes here, that will be less than 0. So that means this x is less than 0, and when x is less than 0, then my function value will be minus x. So this can be written as limit x tends to 0, and this function becomes minus x. So when I put x equals to 0, then I'll get 0. So this is my left hand limit. So let me find what is my right hand limit. So right hand limit is given by limit x tends to 0 plus fx, right? And here this x is approaching 0 from right hand side, so that means whichever number is here, that is bigger than 0. So that means x is greater than 0. So whenever x is greater than 0, my function becomes x. So that's why I have limit x tends to 0. Now this function is x. So this is also equals to 0. Okay, now we'll find what is the value of f0. So f0 means when x is equals to 0, what is the value of function? So when x is equals to 0, the value of function will be equals to 0, right? Because fx is equals to x, so that's why f0 will be equals to 0. So from here we clearly saw that left hand limit is equals to 0, right hand limit is equals to 0, and function value is also equals to 0. Now since LHL is equals to RHL is equals to f0, hence my f is continuous at x equals to 0. So this is all about your continuity. Now we'll check the differentiability case. Now let's find what is our left hand derivative. So left hand derivative means limit x tends to 0, because here the function is breaking at 0, so 0 minus, because it is left hand limit actually. So we have fx minus fc. Fc means f0 by x minus c. C is again 0. So again the case is same as earlier. So when x is approaching 0 from left side, the value of x is less than 0. That's why my function value will be minus x. So we have limit x tends to 0, fx becomes minus x minus f0. And how much is f0? f0 is 0, and x minus 0 is x. So this is equals to limit x tends to 0 minus x minus 0 is minus x. So this is equals to how much? This and this gets cancelled, so only minus 1 is left. So my left hand derivative is equals to minus 1. Similarly, let's check what is our right hand derivative. So right hand derivative is this much. Yes. Okay, now x is approaching 0 from right hand side, so that's why this x is greater than 0. So whenever x is greater than 0, my function value will be x. So fx becomes x. So we have limit x tends to 0, fx becomes x, f0 is 0, x minus 0 is x minus 0. So both are same, so both will get cancelled, so I'll get equals to 1, right? So left hand derivative is minus 1, right hand derivative is 1. Both are not equal. So that's why, since left hand derivative is not equals to right hand derivative, function is not differentiable. So since LHD is not equals to RHD, f is not differentiable at x equals to 0. So pause the video to note. Okay, so now we'll look at our algebra of differentiable functions. Now in all these cases, we'll assume that f and g are differentiable function. Okay, now in the first one, if k is a constant, okay, and I'm differentiating product of a constant and a differential function, then this constant can be taken outside and you can differentiate only the differential function, that is f. Okay, now similarly, when you have f and g as two differential function, and if there's a plus or minus sign, then you can distribute this plus and minus sign. Okay, so that means you can distribute this differentiation over f and g. Okay, similarly this happens and this happens. Now I want everyone to note down this Just pause the video to note down. Okay, so after seeing algebra of differential functions, it's very important for us to know the formula for derivatives of different kinds of functions. Now we have algebraic functions in number 1, so x to the power n, x and constant all comes under algebraic functions. Similarly, we have number 2 trigonometric functions, sine, cos, tan, cosec, sec and cot. And one thing to note is wherever you have c starting letter as c, for example here d by dx of cos x, so it starts with c, so your answer will be in -1. Okay, similarly you have cosec, here we have got negative sign, here we have got cot, and here also we have negative. Okay, now next is number 3, that is exponential function. So there are two formula for exponential function. Number 4, there is logarithmic function. Okay, and in calculus, whenever we see log x, the base of log will be e, not 10. Okay, so it is e. Now the last one is inverse trigonometric functions, which you will learn in chapter 2. Okay, but we'll just write down the formula. So we have a 6 formula in inverse trigonometric functions. Till here is 5, and this is your 6th one. Okay, so pause the video to note down all the formulae. Okay, so now let's have a look at this question. So question says, given fx equals to this much. Okay, so it's also a split function, and you have to examine the continuity and differentiability of the function at x equals to 1. Now just now we proved one very important theorem which said that every differentiable function is continuous. So that's why it's better to go for differentiability first, because if the function is differentiable, then automatically the function becomes continuous. Okay, so instead of checking continuity first, we'll go for differentiability. Okay, so let's start. Okay, now let's check differentiability of this function. Now to check the differentiability, what we need to show is, we need to show that left hand derivative is equals to right hand derivative. Okay, now we know that left hand derivative is given by LHD equals to limit x tends to c minus, and here the function is breaking at 1, so that's why my c is 1. So 1 minus fx minus fc. Fc means f1 by x minus 1. So this is my left hand derivative, and as I said earlier, this x is going towards 1 from left hand side. So this is my 1, and x is going from here, and whichever x comes here, that x is obviously less than 1. So that's why for x less than 1, the functional value will be this much. So that's why my fx becomes this much. So we have limit x tends to 1, fx becomes x squared minus 2x plus 3. Okay, and we need to find f1 as well. So let us find f1. Okay, so to find f1, okay, so we'll see what is f1 from here. So we have f1 equals to, that means when x is equals to 1, what is the value of function? So function value is equals to 2 when x is equals to 1. So f1 is equals to 2. So that's why we have fx, which is equals to this much, minus f1. f1 is 2 by x minus 1. Now this can be written as limit x tends to 1. Let us simplify this. So we have x squared minus 2x plus 1 x minus 1. Now this can be written as, this numerator can be written as limit x tends to 1 x minus 1 whole square by x minus 1. So we have whole square here, we have x minus 1 here, so this one and one of the x minus 1 gets cancelled. So we have limit x minus 1. Okay, so let us put value of x to be 1. So we have 1 minus 1, which is equals to 0. So I got my left hand derivative put to be 0. Now similarly, let's find what is my right hand derivative. So right hand derivative, similarly we have limit x tends to 1 plus fx minus f1 x minus 1 equals to limit x tends to 1. Now this x is approaching 1 from right hand side, so that's why this x is greater than 1. So whenever x is greater than 1, my function value will be this much. So fx can be written as 2x squared minus 5x plus 5 minus f1. f1 is 2. So we have x minus 1 out there. So we have limit x tends to 1. So simplify this. So you have 2x squared minus 5x plus 3x minus 1. Now this 2x squared minus 5x plus 3 can be written as limit x tends to 1. So this can be written as x minus 1 into 2x minus 3 if you factorize them. So x minus 1, so x minus 1 and x minus 1 gets cancelled. So we have limit x tends to 1, 2x minus 3. So we have limit, okay, so let me put the value of x to be 1. So we have 2 into 1 minus 3, which is equals to minus 1. So clearly we see that left hand derivative and right hand derivative are not equal. So clearly left hand derivative is not equals to right hand derivative. Therefore f is not differentiable at x equals to 1. So pause the video to note down. Now let us check the continuity of the same function. Now to check the continuity, it's necessary that we need to show left hand limit is equals to right hand limit, and this is equals to functional value at that point, and that point is 1. So we will try to show this. So first let's take left hand limit. So left hand limit means limit x tends to 1 minus fx. So this is my left hand limit. Now as usual, when x is going towards 1 from left hand side, x is less than 1. So whenever x is less than 1, my function value will be this much. So this can be written as limit x tends to 1, fx is x squared minus 2x plus 3. Okay, so this is equals to, now let's put the value of x to be 1. So we have 1 squared minus 2 into 1 plus 3, which is equals to 1 minus 2 plus 3, which is equals to 2. So this is my left hand limit. Similarly, let's find what is my right hand limit. So right hand limit is limit x tends to 1 plus fx, and this can be written as limit x tends to 1, and this x is obviously greater than 1. So whenever x is greater than 1, my function value will be this much. So function becomes 2x squared minus 5x plus 5. So we have 2 into 1 square minus 5 into 1 plus 5. So 2 into 1 square is 2 minus 5 plus 5 equals to this, and this gets cancelled, so only 2 is left. So my right hand limit is 2, left hand limit is 2, and we need to calculate what is my function value. So when x is equals to 1, my function value is 2. So my f1 is also 2. So clearly we see that left hand limit is equals to right hand limit, and this in turn is equals to functional value, and all these are equal to 2. So since we are successful in showing this, hence f is continuous at x equals to 1. So pause the video to note down. Okay, now let's see this question. So in this question, this function is differentiable everywhere. That means it is differentiable at 1. Okay, because it is differentiable at anywhere means it is also differentiable at x equals to 1. Now we need to find, or we need to show that f dash of 3 will be minus 10. That means the derivative of this function at x equals to 3 will be minus 10. So that's what we need to show. Now the value of x here is given to be 3. That means x is greater than 1. Yes, because x equals to 3 means x is greater than 1. So that's why my functional value will be this much. Now here there are two unknowns, that is a and b. So first we'll try to evaluate a and b. Okay, then only we'll be able to find f dash of 3. Is that clear? Okay, so to find that we'll first find a and b, and it is given that the function is differentiable everywhere. That means function is differentiable at 1. Now we know that since function is differentiable at x equals to 1, then the function should be continuous as well at x equals to 1, right? Now since there are two unknowns here, that's why I need to make use of both the cases. That means function being continuity, so that gives me one of the value a or b, okay, and function being differentiable, so that gives me another value. So let us make use of both cases here. So first let's check the continuity. Now first you need to mention that since f is differentiable everywhere, hence f is continuous and differentiable at x equals to 1. Okay, so let us check continuity first. So okay, so to check continuity, so let's check continuity. Okay, so here since the function is continuous, okay, since function is continuous at x equals to 1, so I can say left hand limit is equals to right hand limit, and this is equals to functional value, that is at x equals to 1. So let us see what is the meaning of this. Now we have left hand limit, which is given by limit x tends to 1 minus fx, and right hand limit means limit x tends to 1 plus fx, and f of 1 means when x equals to 1, when x is equals to 1, what is the value of function? So x equals to 1 is here, so that's why my function value will be this much. Okay, so we have f of 1 to be 2 into x. X is how much? Equals to 1. So 2 into 1 plus 3. So that's why we have, now again this x is less than 1. So x is less than 1 means this one. So my function value fx becomes 2x plus 3. So that's why this can be written as limit x tends to 1, and this fx becomes 2x plus 3. And this is equals to limit x tends to 1, and since this one is greater than this x is greater than 1, so that's why my function value will become this much. So that's why I have ax square plus bx out here, and if you simplify this you'll get 5. Okay, so again if you simplify this is again is equals to 5. Okay, so let me make use of only these two now. Okay, because this is 5 equals to this much equals to 5, so I don't need to use this one here. So let me make use of this one. So let me put x equals to 1 here. So we have 1 into, so a into 1 square plus b into 1 to be 5. So we get a plus b to be 5. Okay, so let me call this as equation 1. Now let me make use of differentiability case. So differentiability. Now since function is differentiable at x equals to 1, what happens? Left hand derivative will be equals to right hand derivative. Now let us put the formula. So limit x tends to 1 minus left hand derivative means fx minus fc, that is f1 x minus c, and c is 1 out here, is equals to limit x tends to 1 plus fx minus fc by fc is 1, so x minus c, that is 1. Now again this x is less than 1, so that's why my functional value will be equals to 2x plus 3. So we have limit x tends to 1, this fx becomes 2x plus 3, so 2x plus 3 minus f1, and what is the value of f1? The value of f1 was turned to be 5, so this can be written as 5, so x minus 1. Similarly this is limit x tends to 1 and this x is greater than 1. So that's why my functional value will be this much. So we have ax square plus bx minus f1 is equals to how much? f1 is equals to 5. So 5, so x minus 1. Now let us simplify this further. So we have limit x tends to 1. So this is 2x plus 3 minus 5. So 2x plus 3 minus 5. So let me write it directly. So 3 minus 5 is minus 2. So x minus 1 equals to limit x tends to 1. So we have ax square plus bx minus 5 here. So we have two variables, that is a and b. Now let me substitute any one of them using 1. So from 1, if I take b, then I have b equals to 5 minus a. So let me substitute b in this one. So we have ax square plus b is equals to 5 minus a into x minus 5. So x minus 1 is there. So let me simplify this further. So we have limit x tends to 1. So 2 can be taken common. So we have x minus 1. So in the denominator also we have x minus 1. So this is again limit x tends to 1. Let me open the bracket. So x square plus 5x minus ax minus 5, x minus 1. We'll group these two together and these two together. Then we'll see that okay, so this is obviously equals to 2. So we have limit x tends to 1, and if I group them together, we see that ax is common. So when ax is taken as common, then from here only x is left, and from here minus 1 is left. Similarly from here I am taking 5 as common, then I'll get x minus 1 by x minus 1. So this can be written as 2 equals to limit x tends to 1. So x minus 1 is common in the numerator, so x minus 1 is taken common. So from here we have ax, and from here we have got plus 5 divided by x minus 1. So I'll cancel these two. Okay, I'll cancel this two, and I'll have here limit x tends to 1 ax plus 5. So basically I am saying that this is equals to 2. So just pause the video to note down. We'll see the next part shortly. Okay, so just now we saw that limit ax plus 5 is equals to 2. So let me put the value of x to be 1 here. So we'll get a into 1 plus 5 equals to 2. So that means a is equals to 2. This 5 goes over there. That means therefore a will be equals to minus 3. So I got the value of a. Now using 1 where we had a plus b equals to 5. So let me put the value of a. So a is minus 3 plus b equals to 5. So that's why what is the value of b? So the value of b is 8. So now redefining the function. So therefore we have fx equals to 2x plus 3 if x is less than or equals to 1, and ax square, that is ax square is minus 3x square, because the value of a is minus 3, plus bx plus b is 8. So that's why this will be 8x if x is greater than 1. Now this is all we have found it. Now question is asking, show that f dash of 3 will be minus 10. So we will check this. So at x equals to 3. So at x equals to 3. So basically at x equals to 3 means x is greater than 1, right? So when x is greater than 1, what is the value of function? Then my function will be fx will be minus 3x square plus 8x, right? Now since we need to find derivative, f dash means derivative, we will make use of two formulae out here. So one is we'll make use of three formula here. So one is algebra differentiable function d by dx of k dot f can be written as k, that's k is a constant which is kept outside, so this can be written as df by dx. This is one that we are going to use. Number two is d by dx of f plus g, so this can be written as df by dx plus dg by dx, so this will be used. And number three will be d by dx of x to the power n, which will be n x to the power n minus 1. So we'll make use of these three formula out here. So differentiating both sides with respect to, okay, so the variable here is x, so that's why I need to differentiate with respect to x. So after differentiating this f becomes f dash of x. Okay, now minus 3 is a constant, so that's why this can be written outside. So let us differentiate only x square, so d by dx of x square. Now this plus can be written separately, and this 8 can be kept outside, and we'll differentiate only x. Okay, if you see here, we have made use of this because this constant has been kept outside here, and here we have made use of this as well because here we have got plus, so that's why we separated the derivatives in both the sides. And the last one, that is this one, we are going to use it now. So this can be written as minus 3. Okay, so this is my n, n is equals to 2, so that's why it will be 2 into x to the power 2 minus 1. So 2 into x to the power 2 minus 1 plus 8 into, we know that d by dx of x, that is derivative of x, is 1. So let us simplify this further. So 2 into 3 is 6, sign is minus, so x to the power 2 minus 1 is x, plus we have 8 here. Now we have seen that f dash of x is how much? This much. Now we need to calculate f dash of 3. So therefore f dash of 3, that means instead of x I have written 3, so that's why I'll get 6 into x is 3 plus 8, so 6 into 3 is 18, and this is equals to minus 10. So that's what we need to prove here. So pause the video to note down. Okay, now let's see this question. So question says, if fx is an even function and f dash of 0 exists, then we need to show that f dash of 0 is equals to 0. Now to do this function, let's try to understand what is the meaning of this first line. So fx is an even function means, okay, so given is fx is an even function. So this means that whenever I put minus x in the place of x, then I'll get again fx. So this is the definition for a function to be even. Okay, so now a function can be considered as odd if the same thing will be equals to minus fx. Okay, but since we have been given that the function is even, so that's why we have this one here. Okay, now again, since f dash of 0 exists, right, since f dash of 0 exists, that means derivative of the function exists at point x equals to 0. So that's why we can say that left hand derivative is equals to right hand derivative. That is, the limit exists and this is equals to f dash of equal 0. Okay, so that's what we can consider. Now let us put the definition for left hand derivative. So this says that limit x tends to 0 minus f of x minus f of c, and c is 0 here, so x minus c, that is 0. Okay, equals to right hand derivative. So right hand derivative says limit x tends to 0 plus fx minus f0, and we have x minus 0 out there. Now there is one more definition, but instead of using that, okay, I'll come to that definition using this particular definition. Okay, now let me introduce one very small quantity, h. Okay, so h is a small positive quantity. Okay, that means h is greater than 0, and we know that since this x is approaching 0 from left hand side, obviously this x is less than 0. Okay, so that's why the x is less than 0 means x is negative number, right? So here I'm going to put, okay, so as I said, h is a very small quantity which is going towards 0, and h is a positive quantity. So here I am writing 0 minus h, because since h is positive, 0 minus h is how much? Minus h, and minus h is obviously negative, because h is positive means minus h will be negative, right? And we know that this x is negative, so x is negative and minus h being negative, both means the same. Minus, since we don't have any x quantity here, it will remain as it is. So x minus, so x again it has to be written as 0 minus h, because instead of x I have written 0 minus h. So here also I am writing 0 minus h, so minus 0 is there. Okay, similarly I am going to do the same here. I am introducing a positive quantity h. Okay, and this x, now this x is going towards 0 from right hand side, so that's why here x is positive. So that's why instead of this x I am writing 0 plus h, because this h is again a positive quantity, so 0 plus h gives me positive quantity. So that's why this is also positive and this full thing is also positive. Similarly I'll write f of 0 out there, so this is 0 plus h. Instead of x I have written 0 plus h, so that's why for this also I am writing 0 plus h, so minus 0 is there. Now suppose if there is 1, then you have to write 1 minus h here. Here you have to write 1 plus h. Similarly you have to write 1 minus h, 1 plus h. Okay, so be careful with that. And similarly you have 1 here, instead of 0 you'll have 1, here also you'll have 1, here also you'll have 1, here also you'll have 1. Okay, so that's how we have got another definition for left hand derivative and right hand derivative, which was mentioned in your beginning session of your differentiability class. Okay, now let's simplify this further. So we have limit h tends to 0. Okay, so far I have not made use of this, I have made use of only these two things. Okay, so we have f of minus h minus f of 0. Okay, and we have here minus h, limit h tends to 0. Similarly we have f(h) f0 by h. Now if I multiply, okay, first let's make use of this here. So f of minus x can be written as f of x, so that's why f of minus h can be written as f of h. So instead of this I am writing f of h, and let me multiply both numerator and denominator by minus as well, because I want to make this positive. Okay, so if I do that, then this minus becomes plus, and here we have got plus sign which becomes minus, so this becomes f of 0 minus this one, and this can be written as f of h, right? And minus into minus becomes plus, so we have limit h tends to this one. Okay, and let me take minus as common here, or let me keep it as it is. Okay, so let me take minus common here. So if I take minus common, then I have limit h tends to 0 fh minus f0 by h. Yes or no? Okay, so we have limit h tends to 0 fh minus f0 by h. Okay, now since it is said that f dash of 0 exists, that means f dash of 0, because we have a definition, f dash of c can be written as limit x tends to c fx minus fc by x minus c. So if I put 0 instead of c, I'll have limit x tends to c, that is 0 f of x minus f of 0, because c is 0, and x minus 0. Now you can substitute x to be h also. Okay, so this is known as, simply if you want to substitute any letter by any other letter, that other particular letter is known as dummy variable. Okay, so instead of x, I'm writing a dummy variable, that is h. It tends to 0, so this x also can be written as fh minus f0. So h minus 0 is h. So basically f dash of 0 is how much? This much. Okay, so which is equals to this one. So instead of this, I can write minus f dash of 0, so which is equals to this also, f dash of 0. So when it goes that side, I'll get 2 times f dash of 0 equals to 0, right? Which in turn gives me f dash of 0 is equals to 0. So this is what we want to prove. So pause the video to note down.